Hi everyone, this is Lasky from Malfind Labs. This video is the third part of this series where we look at the interesting .NET malware sample. So far we managed to analyze the first stage and unpack and deobfuscate the second stage. In this video I will show you how to analyze the second stage capabilities. We will see how to deal with multi-threading, patch the binary, defeat string hashing and code flow obfuscation to understand what the sample is doing. This video will be divided into two subparts because of the amount of material to cover. I hope you will enjoy this video and let's dive into analysis. As a reminder, from the previous video, we got this code, which is the obfuscated code of the second stage of this malware. And this is our main function that we found. So it's our entry point to the code. And what we will do now is find the capabilities, so what this malware is doing, and as you will see, it will also have some anti-analysis techniques that we will defeat. So how we will do it is we will mostly use dynamic analysis techniques. So we will run this code and then check in the memory what it's doing. Why? Mostly because this malware is using some decryption and string hashing routines that I will show you later that basically makes static analysis harder because it's harder to find out some values like string values because they are being generated dynamically when the malware is running and are not really that clearly visible during the static analysis. That's why the main technique we will use in this video will be the dynamic analysis, so executing the malware and observing its behavior. So there is one thing I need to mention before going into the analysis. So what we want to do during the dynamic analysis is basically observe the changing values in the code, and some of these values are stored in the local variables, which we can observe in the locals window. So this will be one of our main source of information. And there is a small issue with it, so I will show you what I mean. I will set up a breakpoint on the very beginning of the code that is executing and run it. And when we hit this breakpoint, everything is fine, code is running, we have a breakpoint, but we don't see a local variable. So we have this internal debugger error. If we refresh it, it changed to some different parsing error, and it will be a pattern. If I go to the further into the code, I won't be able to see any variables, which is an issue. And this issue, I actually not sure what it is related to. I know some other people have similar issues with dnspy, with some obfuscated binaries. So if you know what it is related to and how to solve it, please let me know in the comments. I have one solution to it which I will show you, but it doesn't work with every sample. I know it actually works with this sample, but it doesn't work with every sample. So if I stop it here, and if you remember from previous videos, we have something called like cctor. And in this cctor, we have some anti-tamper methods and decryption of the RVA values in the table, etc., in the function table, etc. So there's some things going on, and probably some of these decryption routines, etc., are messing somehow. That's only my assumption, but probably they are messing somehow with what the dnspy is doing. So I discovered by a pure chance that if I set up a breakpoint here on the very beginning of the cctor and let dnspy initialize everything before this cctor code is executed, I will see most of the variables in the code. So I will be able to see them running the code after that. So let me present it to you. So I set the breakpoint at the very beginning of the CC and I have a second breakpoint also in my main module in the entry point. So if I run the code again, I have a breakpoint in the main, in CC and I actually already see some locals here, which is good. And if we continue the execution, you can see that there is some error. The compiled generated variables can be evaluated, but that's normal for TNSPy. But we can already see that string 0, which is our argument, is basically equals to empty string, but that's fine. We don't have any argument, but we can already see the locals, which is good. So that's the solution I found. It doesn't work every time. It doesn't work with every sample. So if you also have this issue and know a better solution, then just please let me know how to solve it. Going back to our code, we can see in our main function, there are 3 threads starting here. So there's 1 thread, 2nd thread, and the 3rd thread. And each of these threads will have a different purpose and will run a different code. And as you probably know, threads are used to run the code in parallel. So each of these 3 threads will run at the same time. So what's the issue for our analysis here is that once we analyze the code in one thread, the code in the other thread will run at the same time, and they might kind of interfere with each other. So especially as you will see later, one of these threads is running some anti-analysis techniques, which might interfere with our analysis. So we will be analyzing the first thread, and in the same time the other thread will randomly exit our program, because the anti-analysis technique will detect the debugger and will exit the entire program. To avoid this issue, what we need to do is we need to stop these threads from running in parallel, because this will mess up with our code. So the easiest way to do it is just go to each one of these threads and set up a breakpoint at the beginning of these threads. As you can see, I already did that. And same for the second thread, and same for the third thread. So we set up the breakpoint at each one of these threads, and then just continue the execution. And we hit the breakpoint at the first thread. And what we can do now is, if we want to, we can continue analyzing this thread, but at some point, let's say we want to analyze what this method is doing in this thread, we will probably hit the breakpoint in the second thread. But we don't want this thread to go any further, because we want to focus on the analysis of the first thread. So how we can stop the second thread from running, because now if we execute code further, the code will be executed beyond that breakpoint, of course. So we could set another breakpoint further in the code, but that's kind of useless, because we will hit this breakpoint again and then again, and it will be very tedious work. So we can go to debug Windows threads, and here we can see all the threads that are running, and the little arrow shows us the current thread, and we can just freeze this thread. So this thread will be stopped now, and it won't run any further until we unfreeze it. And then we can go back to code of this thread and analyze this thread, for example. And then if we continue the execution, it's the same with the third thread. So now we hit the breakpoint at the beginning of the third thread, and we can see this thread appear here below. So we can freeze it as well. And now, if we continue the code, we actually hit this breakpoint in our first thread. So we can already see these 2 threads are frozen, and only this thread is running. So We can now focus on analyzing this thread, and we don't have to worry about other two threads interfering with our code. So this is how you analyze the multi-threaded application. But since we're already here, we could start analyzing this code and, for example, see what this method is doing where we put our breakpoint. It's not that much interesting. So if we click on it, we can see it's taking some integer argument and passing it to the sleep function. So it's basically like a wrapper around the function, and you will see this a lot in the code. So this is kind of an obfuscation that ConfuserX is also doing. So for example, here you can see the method 95 is a wrapper around the kill function. The method 96 is wrapper around the sleep function, etc. So what we can do to make our code analysis a little bit easier is just rename this routine. So we can just call it a sleep wrapper. And then if we stumble upon this function again in the code, we'll already understand what it's doing. We can do this same with the other functions if we want, or we can do it once we stumble upon them. That's the easier solution because there's plenty functions here. As you can see, it would be hard to go through all of them and to rename them. We could potentially write some automation for this, of course. So this is the sleep wrapper, which sleeps for 5 seconds. It's not that interesting. What's interesting for us in this thread is the code inside the infinite loop. So there is some functions here, and I will show you what they are doing. But before we go into that, and as you can see, we already can see that there is a sleep method, for example, here as well, because we renamed the function. So we already see that it's being used in the code again. So renaming is really important. So please do it during your analysis. And going back to analyzing our code, before I will show you what this thread is doing, I need to speak to you about two things. And the first of these things is this method 0. Because this method 0 is quite important for us throughout the entire code. And why it's important? It's because it's doing something which is called the string hashing. So if you don't know, the string hashing is the way to obfuscate the strings and take the strings, generate the strings dynamically in the memory. So the strings are put in some sort of hashing table, and where the specific hash is provided, the string is returned. So this method is taking some number and it's returning a string. And how do we know this method is doing that? Well, if we go through this code, it becomes obvious after some time. So it's just a matter of basically like a static analysis going through the code. So as you can see, this method here is getting some string as an input. And it's doing something with this string, assigned to a different string. And for example, we have this method here as well. So we can see this other method is also taking a string. And in that case, it is assigning it to the process start information, for example. So if we go through the code like this, it will become quite obvious. This method kind of need to return some interesting string for us. So we can analyze this method. And if we go here, we can see this. This method is doing calculation. And after this calculation, it's returning one of these two values. So if we actually go to the first method here, what we can see, there is a dictionary here declared in the class 11, static dictionary in the class, which this method is trying to get some value from. And this is already interesting because the hashing function is usually using some kind of dictionaries to store the hashes pair it with some corresponding string. So we can use this and see if it's actually interesting for us. So there is also some kind of a text variable here declared, and this is our outcome variable for try get value. So this is already interesting, and if we set the breakpoint just after this dictionary tries to get value to our text variable and run our code, then just need to change variable to locals, and we can see we hit the jackpot. We can see this variable is now holding the text localhost, which is something interesting for us because it's clearly some kind of a string that the malware author didn't want us to see being stored directly in the code. So we already know that here the variable local will be used. So the variable local will be passed to this method and something more will be done with it. And before we dive deeper into the analysis, you know what we need to do. So we need to edit the method and rename it just so we know what it's doing. So this method is actually getting a value from the dictionary. And this is more important for us because this method is used a lot in the code. So we will rename it as a get string. Actually, we can prepend something at the beginning, so we know this is the method coming from the malware itself and not some kind of a library function or something like this. This is just a naming convention that will make our life a little bit easier. So now we can see this mal get string method is used in the multiple places, and then we can find which kind of which kind of strings it is returning. Knowing this fact, we could start to analyze our main thread code, which is in the infinite loop. But there is still few things more to do, but let's start from the beginning. So we could already try to make sense of this code. There's actually not that much functions in here. So there are a few functions, and we can see that, for example, here we have some enumerator being declared. And what this enumerator take is, or we all can already see it's getting some processes. So there is this method 92, which is basically a wrapper around the get processes. So we could just rename it as a get processes wrapper. And it's quite clear that this enumerator basically enumerates over the processes. So then there's a while loop where we have just a wrapper around move next. So basically iterating over this enumerator. So we'll call it move next wrapper, and then we have this process variable that it's being assigned the current value of the enumerator, and then this process variable is passed to this method 93, which basically takes the it takes the start info of the process. So process start info, let's call it get process start info. Yeah, I know I'm inconsistent with my naming convention. So there is some method 94 that takes a process start info and then takes some string, and it assigns it to this start info verb variable, or structure actually. So we can also rename it to process start info verb assignment or whatever, just so it be clear what it's doing. And then we have some switch statement, which we will discuss soon. That's actually the second thing I wanted to discuss with you, but we will discuss it soon. And then we just had this sleep wrapper and only one more method that we don't know what it's doing. And it's also quite clear. It's a wrapper around the key method. So it basically keys this process that it's being passed in here. So let's call it a key wrapper. And with all this renaming, I think it's already quite clear what's going on here. So this method is looking for some kind of processes, most likely, and then if it finds them, it kills them. That would be my assumption. Actually, I know it because I analyzed this code already, but even if I analyze this code for the first time, that would be my assumption seeing these functions already. So there is only one more issue here. There is this if statement here. And this if statement is checking something, and it will run only the code while it's true. So if this if statement is not true, it won't run this code. And unfortunately for us, what this if statement is checking, so it's quite unclear here because this part of code is a little bit not visible for some reason for the dnspy. So there is some parts of code that are not clearly visible in here, but it's basically creating some class here and assigning this string here, and this string will be the localhost, and then it will return this class. And we can also see some structures being assigned here, and especially this is interesting: VTS active, VTS connected, VTS shadow, etc. So this is actually recreating a specific class that I will show you soon. But basically this class is then returned to this enumerator and is being enumerated here. So if we go in here, we are actually here right now. So we can just step over this code, and then we can step in, and we are in the any enumerator. So we are actually here. So this any enumerator is received this class that has been created, and this class has this string localhost that we already saw. And actually, if we look at the results view, there is one result which is of the class 9, which also has been created by this malware. Sorry if it's confusing for you, but it's actually not that clearly visible in the dnspy for some reason. But if we look at here, we can see that there is some name, which is actually my machine name, and there is some other string, which is my username, and then it says VTS active. And if we Google for the VTS active string, we can find in the Google that this is part of the VTS API class, which is related to the remote desktop services, and the VTS connect state class enumeration actually state that the VTS active means a user is logged into the WinStation. These states occur when the user is signed in and actively connected to the device. So this basically tells the malware that there is some user connected via remote desktop, and this is because I'm using Hyper-V and kind of connecting to it remotely. So this check will always be true because it actually checks if there is something in the enumerator, and if there is anything in the enumerator, it will return true, and it will actually not execute our code. So we run just directly here. So this is an issue because we cannot dynamically analyze this code. So how we bypass this issue when we want to dynamically analyze a code, but there is an if statement that we cannot pass because for some reason it's always true and the code is taking a different path. This is a typical issue in the reverse engineering, and one of the solutions for this is to patch the binary. It's the solution that we cannot always use because sometimes it will crash our code. So to patch the binary means basically to change this if statement. So right now, if anyone is logging into the workstation, this is returning true, but there is a negation, the exclamation sign at the beginning. So it will actually be, the entire statement will be false. So this entire block of code won't be taken. Yeah, that's basically this. So what we want to do is we want to reverse this if statement. So patch the binary for it to reverse this statement. And in this case, it will work because it will only trick the malware to think that no one is logging into the workstation. Actually, it will just take this if statement if anyone is logged into the workstation. So this will be fine. There are some cases when this kind of approach won't work. So the simplest scenario is where the if statement is safeguarding some part of the code to not run into the exception. So the easiest example is, for example, the if statement checking for some numeric value to not be 0, because after that it's dividing by this value. So of course, if we patch this kind of if statement and reverse it, for example, then our code will obviously crash. So this kind of approach is not always working, but in that case it will work. So I will show you how to do this in the dnspy. So actually what dnspy is doing is generating a kind of like a decompiled code from the intermediary code. So I'm not gonna go much into the details here because it's maybe a topic for different video, but C# is a managed language that has an intermediary code, and the intermediary code is actually being interpreted by the C# interpreter, etc., C# virtual machine. So yeah, not going much into the details. We can right click here and say edit ER instruction, and this is how the intermediary language is actually looking like. So this is what this binary is actually looks like. And the representation we are working with is just the representation that dnspy is generating based on this code. So this code is kind of like an assembly code and a little bit more advanced than the assembly code, but in general it's like an assembly code, so it's being executed instruction by instruction and have different opcodes, as we can see here, and the different operands. So we can actually modify the opcodes here, and this will patch our binary. So what we can see here, we have some calls here, and then we have something which is called brtrue, which basically means branch if true. So this will branch to the instruction number 77 if the statement above is true. So the statement above will return some value on this and on the stack, and if it's true, then it will branch to this instruction, and we can already see this instruction. It says leave as, so it's a different opcode instruction. And if not, it will proceed with the code. So it's a typical branch instruction used in the if statement. And what we can do here is basically change this opcode to say br false. And now what it will do is only branch to this instruction if the statement above is true, and if it's false, sorry. And if it's true, it will continue with the execution. So we basically reverse our code. And if we click OK now, we can see, I don't know if you see it, but our exclamation mark disappeared. So it means now this statement is not negated, and it will basically continue the execution if this entire code is true. So that means if anyone is logged in, it will continue the execution and not stop the execution as before. And there is one big and important disclaimer here. And this is something I stumble upon a lot, and I know that many people who work with dnspy and the .NET code also have issues with. So if we patch the code like this and change the AR instruction and run the code again, so let me, for example, set a breakpoint in here and execute this code again. And as you will see, we are again on the sleep wrapper, so the breakpoint was not hit. So how is it possible we change this instruction? It should go here every time now. The issue is, even if the dnspy is now showing this instruction is modified, it actually isn't, because it's executing the code that is on the disk, and this code is not yet modified. So what we actually need to do is save this binary after every change. So we can close it, and then it asks us if we want to save this file. And if we want to save this file, we can save it as this, but add something like mod, meaning it's modified. And then we can go back here, and we have our modified file in here. So we can load it back to the dnspy, go to the entry point, and go to our first thread, our second method, and we can see now this if statement is already reversed, and now we should be able to hit this. Actually, I didn't stop the execution before reloading the binary, so right now we can put, after stopping the execution, we can put the breakpoint here. Unfortunately, we need to do a few more things, so we need to go back to our sysiter, as you remember, put a breakpoint here as well. We also need to go back to our entry point and put the breakpoints on the two other threads so they don't interfere with our execution. This is what we already discussed. And now we can actually run our code again. Then we hit some of our old breakpoints. This is the breakpoint in the second thread, so we will actually freeze it. And this is the breakpoint in the third thread, which will also freeze. And then if we continue with our execution, we are on this if statement. And if we step over, voila, we are inside the if statement. So we patch the binary and we managed to bypass the if statement that wouldn't allow us to execute this branch of code. So now we can analyze this code, and we already made some initial static analysis on this, and there's actually one more function we didn't analyze, which is quite important, and it's in here. It's the method free. So this enumerator is actually getting the processes and is applying the where statement, which basically filters only the processes that are equal to some statement in here. So it will filter only the processes that are passing this Boolean expression function, kind of. So let's see what it does. And this method is getting a process structure as an input, and then it's doing few things. Actually, there's plenty of things going on in here, but as you can see, they are all very similar. There's method for, then method 3, then method 2, and then malgetString, which we already know is getting some string from the hash table. So all these methods here are quite similar, and what we can check is method for. Very simple. It's a wrapper around the contains method. So it checks if the string 0 passed in here as a first argument contains the string 1 in it. So it basically compares the strings. So we can rename it as a contains wrapper, just so we clear. And then the method 3, it's just a wrapper around to lower. So it just change this string to lowercase. And the last method is method 2. It's takes the process structure and gets the process name value from it. So it's just more get process name. Simple as that. So as you can see, it's quite simple. It's getting some process name, it converts it to lowercase, and it compares it to this string that is being returned by the getString function, which takes it from the hash value. So it looks for some kind of process, and then remember, this is our filter class. So it actually passes all the processes that are running, but filters only this one that passes this check in here. So what it does, it will return as true only for the processes that are matching some strings in here. So we can actually see what it looks for, and the best way to do it is just put a breakpoint at the contains function, because then it will show us exactly what it's what is it looking for, and what it found. So let me run the code now, and we hit the breakpoint. And we can clearly see in our locals here, which is really nice, the string 0, which is basically our first process on the list of all processes running in the system is svc host, and the string one is anydesk. And as we can see, if we go back a little bit, the string one is the second string passed to the contains wrapper function, which is the one that is being returned by the getString function. So this is what the malware is looking for. So it is looking for the process called anydesk. And if we go further, there is another contains wrapper that looks for the similar process, but now it looks for the TeamViewer. And the third one is looking for the process name UltraViewer. And there's also a fourth one that is looking for the process name Amy. And the next one looking for the process called anydesk. And it goes around. So it looks for the TeamViewer again, and it goes through the entire list of the processes like this. So now it's the second process from the list, which is logon UI, and it's looking for anydesk, TeamViewer, UltraViewer, etc., and the next process, etc. So basically, I hope it's quite clear what is going on here. So it's looking for these different remote process tools. So, and if it finds anydesk, TeamViewer, Amy, or UltraViewer, any of these, it will do something with them. And what it will do is, let me go back, is it will pass it here. So it will assign something to the verb string. We don't know which. We would need to run one of these processes to check, or again patch the binary to bypass this, but bypassing the enumerator is a little bit more complicated, and then it will kill it. But we don't need to do much more. I think it's pretty clear what this code is doing. I already explained it to you, but now I hope you can see it also based on our analysis. It's looking for four of these remote access tools: TeamViewer, Amy, UltraViewer, anydesk. And if it finds any of it, it kills these processes. So it basically don't like the remote access tools being running on the machine when the malware is running. This concludes our first threat analysis. So it basically verifies if anyone is logged into the machine, and if not, it looks for these remote access tools and kills their processes. So that's the purpose of the first thread. So we can rename this method just so we know what it does. I will name it kill rats because it's killing the remote access tools. And now we have one of the three threads analyzed. We can move on to analyze the second thread. To do this, we will need to go to threads. I will stop the first thread, freeze the first thread, and unfreeze the second thread. So now we can focus on analyzing the second thread. And we can see this method one is basically passing something to another method. So it's passing some kind of string. So it's decrypting some kind of string, passing it to this method 91. And this method 91 is doing something. Let us put the breakpoint in here. And let's run our code. And it stopped here, and we can clearly see that the string is passed into the into this method is a string Microsoft Remote Service, and if you remember from my previous video, if you watch the previous videos in this series, we have a first stage malware that was registering a service called Microsoft Remote Service, and then this service was downloading this second stage malware and executing it from time to time. So actually I have this sample still here. If we go to this first stage malware, we can see that this Microsoft Remote Service is being registered in here, and this basically is responsible for launching this second stage malware. So it's like we already analyzed it, right? It's downloading the zip file and creating a new process that is basically running this Windows desktop service. So this is clearly something to do with this. So let me go back to our method 91 that we are analyzing right now. We have a breakpoint in here, and so this is passing this Microsoft Remote Service. So this is something to do with our previous stage of the malware, which is interesting. And we have a few methods in here, and the first method is just a wrapper about creating a new service controller. I will rename it, go back here. So we can see the new service controller is being created, and there's something being done with this service controller. So actually there's one more thing I wanted to show you. It's about these case switches. You might be wondering even before what these case switches are doing. But yeah, let's discuss them really fast. So these are basically obfuscating the flow of the code. So case switch, in case you know, it's like, in case you don't know, it's like a bigger if statement, kind of. So it's taking some variable, and based on the value of this variable, it's executing one of these four cases. And normally it's something like switch this number 2 variable, and if it's equals to 2, let's go to, actually maybe if it equals to 1, it goes here. If it equals to 3, it goes here. If it equals to 4, it goes here. And here it's the only more complicated thing is that they put these big numbers for us to not see directly what is being executed. So if we actually want to know which code will be executed first, we need to do some calculation. We can do it in the calculator, Python, or there's something called C# interactive in the dnSpy, and you can actually do some calculations in here as well. So let's take our num variable and copy paste it. Sorry, we need to initialize it. This C# interactive is unfortunately not in the context of the running code, so we need to initialize all the variables again if we want to use them. And yeah, sometimes it's not that easy. And then we can actually make this calculation, which is here. And what this switch does is calculate this value. So the value, as you can see, the result of this calculation is 1. So we can clearly see now the first case it will take is the case 1u. The u is only it's an unsigned integer, doesn't matter in that case. So it will take this path first. And what this line does here is a few things actually. So we have some value assigned to the variable num, and we know this variable num is used in here to calculate the value that will tell the switch statement which code should it execute next. So this entire expression here will be evaluated to some number that will be later used to choose the next path for our code. So this is first thing. Second thing is this expression here. It's like a shortcut if statement. So if you don't know this, C# has this kind of a shortcut if statements where there is a some condition, then the question mark, then first branch of code that tells what to do if it's true, and then else something else. So it's basically like if this, then do this, else do this. So the question mark is separating condition from the first line of code, and the colon is like a else condition. So basically, if this is true, this entire expression will be evaluated to this number, and if this is false, this condition will be evaluated to this number, and then some additional calculation will be made, and all of this will be assigned to this num variable, and this will be used to choose the next path of code. So I hope this is clear how this kind of switch works. So let me show you this in practice. Maybe it will become more clear. So first of all, what is our condition here? So our condition is if something returned by this method 171 is not equal to service controller status stopped, then the condition will be true. Otherwise, it will be false, and it will evaluate to this number. And if it's true, it will evaluate to this number. So this method 171 is just a wrapper around the service controller status. So we can just rename it to market service controller status. And so it's pretty clear, I hope, from this code that it checks the status of the specific service we discussed already, the Microsoft Remote Service. And if this service is not stopped, so it's running, it will evaluate to this number and choose some code path. And if it's in the state stop, it will evaluate to this number and choose some different path of the code here. So this is how this obfuscated switch statement works. So let me show you this. So let me show you first what happens if this switch statement, if this condition is evaluated to true, which means the service is not stopped, which means the service is running. So our num will equal to this first number because our condition was true. XOR num2 times this big number, and basically it will evaluate to this kind of a big number, but then the code will continue and will return to the switch statement because of our infinite loop. So this time our num is equal to something else, so the switch statement will have different value. So let's see what it is. And the value in this case will be 2, which might be a little bit surprising because we have only case 0, 1, 3, and 4. But if you think of it, it's not that surprising. So if the value is 2, it will go to the default value, which is go to block 3, which is basically escaping our for loop. So if the service is running, it's like a desired state for this malware, so it doesn't want to do anything more. It just check, okay, service is running, everything is fine. Let's go out of this for loop and let's just sleep for 2 seconds, and then check again. So I hope it's pretty clear for you. And then now check what will happen if the switch state, if the service is actually in the status stopped, so it's not running. Then this condition will evaluate to this number. And just one thing to remember, I always also forgot about this. So calculating this value here, we actually changed the value of num2 to something else. So now it will evaluate to this number, and it should evaluate to a different number when we were here. So we changed some numbers, so now our calculation might be wrong. So just to reset it to the state it should be in, we will reset our num to the previous value, and we will calculate the condition once again, which will also change our num2. And now we see we are again in the case 1. So our variables are now in the state there should be when we are in the case 1. So now we can make our calculations once again. So the num will be equal this time. It will be equal this time to this value because the service is stopped. XOR num2 times this, and this will be equal to this value. And if we recalculate our switch, it equals to 3. So if this service is not running, if it's in the status stop, it won't go out of the loop. It will go to the case 3 actually. And the case 3 is some method 172, which is basically wrapper around the service start method. So service start wrapper. So it's pretty straightforward. It checks if the service is stopped, and if it's not stopped, then it doesn't do anything. If it's stopped, it will restart this service, and then it will recalculate this number. So our num will now equal to something else, which is this number. And then if we recalculate our switch statement once again, because we will make a loop, now it equals to 4. So we can see now after the path, this path, it will take this path, and this path is having method 173, which is a wrapper around wait for status method, which is basically waiting for the service to start. Wait for status wrapper. So now it waits for the status to change to running, and then it recalculates our num variable again, and now it goes to 2. So it restarted the service, and it goes back to the loop and out of the loop, and it will sleep for 2 seconds, and after 2 seconds it will do this again. So it's a little bit lengthy explanations, but I hope now it's clear for you how this switch statement works. So I wanted to explain on this one because this one is pretty straightforward and easy to explain, but this is basically how this control flow is obfuscated. It's kind of, I think it's one of the ConfuserX features. There are some tools that will try to remove this switch statement and just evaluate them like I did right now manually and change the code appropriately. But yeah, they sometimes break the code and we cannot run the sample. So it's easier to do it manually. It's actually not that easy and you don't have to calculate it every time. Sometimes it's pretty clear what will be going on. So we don't even have to do this calculation here. I only wanted to show you how to do this because it's quite clear that the malware will first check if the status is stopped, then it will restart and then it will check for the status to be restarted. So this concludes our second thread analysis. So this thread is basically restarting the service. We can call it a service watchdog because it basically checking if the service is running and then it's restarting it. So kind of like a watchdog service. So we have the third thread to analyze, and this third thread is kind of a more complicated. It has some anti-analysis skill, plus it does some other things. And because this video is already very long, I actually planned to be half this length. I will leave this third thread for the next part of the video. So if you're interested, I will release the next part of the video hopefully soon, and we will discuss what the third thread is doing. I think it's the most interesting one because it has some anti-analysis techniques to beat. This is the end of this video. We learned how to patch a binary in the NSPY to redirect a float of the code. We understood string hashing and understood how to deal with multithreading. We understood case switches and how they are used to obfuscate code flow. This allowed us to see how this sample is detecting and killing remote access tool processes and how it's keeping malware service alive. In the next video, we will look at the third and the final thread. We will understand the anti-analysis techniques implemented there and defeat them. I hope you enjoyed this video and see you in the next one.